Hello learners, in this lecture we'll try to take one more problem on the mixed design and we'll try to understand that. So this is a question what we have. This time we need to design our concrete for M40 grade of concrete. The type of cement is OPC, ordinary Portland cement of 43 grade. Type of mineral admixture, we are making use of mineral admixture in this particular numerical. So he's telling us to make use of fly ash. Maximum nominal size of aggregate is 20 mm. Minimum cement content is 320. Maximum water cement ratio is 0.45. Again, they require a slump of 100 mm. Exposure condition, it is severe. Method of concrete placing, they're doing it with the help of a pump here. Then degree of supervision, it is good here. Type of aggregate, crushed angular aggregate. Maximum cement content is 450 kg per cubic meter. They are going to make use of super plasticizers, and rest all things we have already understood. Now the first thing, always the step one will be target strength for the mixed proportioning. How do you do that? The formula is straightforward. F dash ck is equal to fck plus 1.65. Fck, they are asking us to do it for M40 grade of concrete. So 40, it will be, I'll write it here, 40, yeah, plus 1.65, and S is a standard deviation. For 40 grade, the standard deviation will be 5, I guess. Let me check it out. Go to the next. Yeah, the standard deviation is 5. Again, we'll quickly go through that if someone is finding it difficult to understand from where we are getting this. Yeah, so for that M40 grade, standard deviation is 5, right? Yeah, this is done. Next, we are getting, if you do that, we are getting 48.25 Newton per mm square. What do you mean by this? Even though I'm assuming my grade to be 40, but when I do that mixed design, no, this will be my target. Always I'll go for a more target, because concrete and all, you cannot predict the nature of a concrete. So always as engineers, we try to be on a more safer side. So this is my target. So when I target for 48.25, at least I'll end up by getting more than 40, right? It's like, suppose in the examination, if you want to target for 100 marks, 100 out of 100 marks, huh? Then you cannot learn only 5 chapters and go, right? You have to study 6 or 7 chapters so that you can score 100 out of 100 marks, isn't it? Only by studying 3 chapters, it's not possible. So at least if you want to score 100 out of 100, if you have 8 modules, right, at least 6 to 7 modules you need to learn properly so that you can get this. So this is a targeting is for 100. If you want to get 100, then you have to put more efforts. That is the reason we always go in this way, 48.25. So 40 is what I require, but I get 48.25. Yeah. So once this is done, next step is again very simple. Next step is selection of water cement ratio. So we know that maximum water cement ratio is 0.45, which is given in the question. So based on the experience, you can take it as 0.40. Again, as I mentioned, you need not take it 0.40. You can take any value here, but maximum it should not go beyond 0.45. So as per IS 456-2000, these are the things what we have. For mild, it is 0.55, moderate 0.5, severe 0.45, and so on, right? So if you're not able to understand from where it's coming, try to follow my previous lecture where I've explained it in detail. Again, I'll not explain in detail for this lecture as well. Exposure severe condition, what we are considering is 0.40, which is less than 0.45, hence it is okay. So again, if you want, I'll go for the exposure condition. Yeah, so this is the exposure condition here. For the severe exposure condition, we are referring RCC now. For severe exposure condition, maximum free water cement ratio what you have to take is 0.45, and that's what we have done it here. Yeah, right. So 0.4, what we assume, maximum is 0.45, which is less, hence it is okay. Next is selection of water content. Now again, refer table 2 of IS10262. Note down the value of quantity of water content for 20 mm aggregate, right? So here, what is the slump that is required? So here the slump what is required is for us 100 mm. 100 mm is the slump that is required for us. So for 100 mm slump, what is a, and for 20 mm corresponding aggregates, you have to refer this particular table. I'll take you to that table. See, it's given here. We have 20 mm aggregate, and corresponding to 20 mm aggregates, the maximum water content what I can use is 186, right? But this table what we have, no, but this table what they have prepared, this table is prepared for angular aggregate and for the slump value of 50 mm. That's it. This table is valid. But in our question, that slump what we have got is 100 mm, right? That means we cannot directly take this 186 value. We have to do some correction factor. Now, what is the correction factor? The correction factor says that for every 25 mm increase in the slump, you have to increase this value by 3%, right? That's it. For every 25 mm increase in the slump, increase this value by 3%. Now from 50 to 100, what is the increase? From 50 to 100, the increase is 50, right? 50 plus 50 comes out to be 100. So if for 25 it is 3, for 50 how much it has to be? For 50 it has to be 6% increase. That's it. The same thing you can see here what we have done in manual calculation. I'll take you there. Yeah, so here you can see the for estimated water content for 100 mm slump will be 186 we got from the table, plus you add 6% to that. 6 of 100 into 186. For this 186 you have to add 6%. Okay, it comes out to be 197 liters. Now we are using a super plasticizer, so the water content can be reduced up to 30%, right? Now but practically when you make use of SNF, so when I say of super plasticizer, no, I'll write it here. Yeah, so the plasticizer what I'm supposed to use is usually what we use is SNF, that is sulfonated sul yeah sulfonated naphthalene formaldehyde. Okay, this is a super plasticizer what we are going to use. So it has been found that up to 29% of water can be reduced here. 29%. Now again, as I mentioned, it depends on what from which company you're bringing the super plasticizer, right? So based on the company also it all depends, but here we'll take it as SNF, and let us say 29% there is a decrease in the water. If 29% there is a decrease in the water, percentage of water content will be 100%. Full, here we are taking full, right? So 100 minus how much you are going to do the reduction? 29%. 100 minus 29 comes out to be 71. Now hence this water has to be reduced by 70. I mean, you have to take 71% of this water. So hence the arrived water content will be 197 into 0.71. That comes out to be 140 liters. That remaining water what you want, no, that you are going to get from super plasticizer, because that super plasticizer is going to give me 30%, 29% of that, right? Yeah. So now calculation of cement and fly ash. Yeah, here you have to understand one thing. In the previous lecture, what we had done, we had calculated only the cement content, but here this time we're making use of fly ash. So fly ash is a pozzolana. So it all depends how you want the mix design and all. In the question itself they have given that you have to make use of fly ash. So now both are my cementatious content. So hence cementatious material, that is cement and fly ash together will be, how do you find that? Again, it's a very simple calculation that you need to follow. I'll do it. That we know that water cement ratio, we know water cement ratio what we are adopted is 0.4. We have got water from here 140 liters. Zero point 0.4 is ready for us. So with this, if you cross multiply, we'll get cement content, therefore cement. But here this is not cement, it becomes cementatious material, because this C contains your cement plus fly ash together. So what you're supposed to do, water content, what is water? 140, you divide it by 0.4. 0.4 is my water cement ratio. Try to do it manually, you're going to get the answer as 350 kg per cubic meter, right? That's it. So once this is done, now come back here. As per IS 456-2000, for RCC work, minimum cement content for exposure of mild it is this much, moderate it is this much, and so on. What we are referring is ours is a severe condition, right? For severe condition, what is the maximum, what is the minimum cement you have to use? 320. If you're not able to follow here, go back here. For the severe condition, you have to make use of 320 is the minimum cement content. And how much we are getting? We are getting 350. So my 350 is greater than 320, hence this is also okay. Now there's one more catch here. Since we're using a cementatious material content, no, what you can do, no, you can increase this by 10%. Whatever answer you're getting, that 350, you have to increase it by 10%. So for cementatious material content is equal to 350 into 1.10, which comes out to be 385 kg per cubic meter. So if you're increasing this, then again what will happen? There will be a change in the water content. So water content is 140. Now this time your cementatious material content has gone to 385. So the water cement ratio is equal to how much? 140. You divide it by 385. You're going to get 0.364, right? I hope up to here it is clear. Next we'll go to step 5. Before that, now as I mentioned, this 385 is what I'm getting, no, this includes my cement as well as fly ash, but I need to exactly know how much cement and how much fly ash out of this. So for that, what we usually tell, we usually say 30% of that we are going to make use of fly ash out of the 100%. That means out of 385, in this 30% we'll add fly ash, remaining will be the cement. So fly ash at 30% of the total cementatious content will be how much? We got 385. Take 30% of that. 30 divided by 100 comes out to be 115 kg per cubic meter. Therefore 115 kg per cubic meter is my fly ash. So therefore cement will be total content, that is 385 minus fly ash will give you the total cement content. So this 385 is the cementitious content. Out of that, if I deduct the fly ash content, this 270 what is left out, this is my cement content. Altogether 38, altogether it is cementitious. Yeah. Next is step 5, proportion of volume of coarse aggregate and fine aggregate. The moment you come here, two things you need to understand. First is try to see the question given in which zone is your fine aggregate. So it's given here fine aggregate conforming to zone 1 of table 4. So it is conforming to zone 1. The moment you see this zone 1, you have this table. Yeah, you have this table. Okay, now try to find. See, for this you need to understand what is the maximum aggregate size. Here always we are using 20 aggregate size is my maximum. Let me go back. Yeah, so 20 is my maximum aggregate size. So this is a table, this is a row I need to look. What is the zone given? The zone given for our question is zone 1. So corresponding to that, you check a value here. That means corresponding to zone 1, and for 20 aggregate, I need to take how much? 0.6. This is 0.6. Right, you can see here this is 0.6. But again there is a catch. This particular table what is prepared, no, based on the experience of the research people, this is considered by taking water cement ratio 0.5. For water cement ratio 0.5, this particular table is prepared, but the water cement ratio what we have adopted is 0.4, isn't it? That means again we have to put a correction factor. Now what is that correction factor? That we'll try to see here. Yeah, so that correction factor what we need to consider is this one. So for water cement ratio of 0.5, we got answer as 0.6, isn't it? But our water cement ratio is 0.4. For that, how much value you have to take, right? So for that, you have to put this correction factor. The correction factor is that for every 0.05 increase in the water cement ratio, I'll read it once again. For every 0.05 increase in the water cement ratio, you have to decrease the above value, that is this value, no, this value what you're getting 0.6, you have to decrease it by 0.01. That is for every 0.05 increase in the water cement ratio, you have to decrease the above value, that is this value what you get from the table what we saw, no, 0 point, that you have to reduce by 0.01. But again there is a catch here. So if you see this table what we have, no, it is prepared for 0.5. Our water cement ratio we got is at 0.4. That means from 0.5 to 0.4 we have come down, no? If we have come down, then this value has to be increased. Okay, one way of understanding. Let us say the table what is prepared is for 0.5, but I got a water cement ratio of 0.55. Now from 0.5 to 0.55 we are increasing, I mean we have gone up, right? So if we have gone up, then the value what you're getting, no, this value, then you have to decrease that value. It's vice versa. If water cement ratio goes beyond this 0.5, you have to decrease this value. But if your water cement ratio is less than 0.5, you have to increase that value, right? Now from 0.5 to 0.4 the water cement ratio has come. Therefore there is a decrease of how much? From 0.5 to 0.4 there is a decrease of zero point 0.1. So since there is a decrease, we have to increase the value. So we need to increase the value of I in the sense this value. Okay, this value. Now to put it in a better way, let us say last time also we referred the same problem. Now let us say uh, yeah, so let us say this, no, let us say this is not zone 1. For example, let us say zone 3 is given here. So if zone 3 is given, so what would have happened? I have to go back here. Corresponding to zone 3, we try what is given here. So corresponding to zone 3 is here, right? This is my zone 3, and this 20 answer will be 0.64. This time you should have taken 0.64. Suppose if zone 3 was given, so we'll take 0.64. Then what would have happened? Then here instead of 0.6 I would have written 0. How much it is? 0.64 I would have written. I would have written 0.64 here. Then based on that your values would have changed, right? In this way you need to carry out that. Yeah, so I'll erase everything. Yeah, so I hope up to here it is clear. Yeah, so now what we are supposed to, we need to increase the value by 0.01. So for 0.05 you have to reduce it by 0.01. Therefore for 0.1, because here there is a decrease of 0.1, no, how much you have to do? It's very simple, cross multiply. For 0.1 decrease, okay, 0.1 into 0.01, then you divide this by 0.05. So you are going to get 0.02. That means For corresponding to 0.4, this value will come out to be 0.02. Okay, this will come out to be 0.02. I hope you have got an idea how it has to be done. Just in case if you have still doubt, you can put it in the comment box. I'll explain it there, right? So this 0.02 will come. So this answer, to get this 0.02, you have to apply this method. That's it. For 0.05 increase, I have to decrease my that above value, this value, by 0.01. That's it, right? Yeah. So 0.02 we need to take. Now what they have done after this? So that is why you can see the value written here. They have got 0.02. Therefore, the corrected proportion of volume of coarse aggregate for the water cement ratio will be 0.60 we got from the table. For that, we have to apply a correction factor of 0.02. So 0.6 plus 0.02 comes out to be 0.62. Therefore, the volume of coarse aggregate is 0.62. But again, in the question they are told, they are going to do the concreting by pump. So if you are going to do the concrete by pump, where it is given? It is given here. Pumping method of concrete placing is pumping. So if you're doing a pumping, then we want more fine aggregate. So that is why, therefore, for pumping the concrete, this value should be reduced by 10%. Now again, this 10% you can even reduce it by 8% also, or 9 or 10. It depends, but the code is telling based on the experience you have to reduce it by 10%. But again, depends on the site conditions and all how much you want to reduce. But here we'll take 10 only. Therefore 10, 100 minus 10, if I do, no, 90% of the above value you have to take. Therefore, the volume of coarse aggregate will be 0.62 is actually what we got, but we'll reduce it by 10%. So 90 divided by 100, which will come out to be 0.56. If this is 0.56, then what will be the volume of fine aggregate? If a volume of fine aggregate will be total will take 1. 1 minus 0.56 if I do, I'll get 0.44. Right, that's it. So if you add this 0.56 plus 0.44, which will come out to be 1, that is a volume of coarse aggregate and fine aggregate. That's it. Next, coming to the mix calculation, volume of concrete always we speak in terms of cubic meter. So it is 1 cubic meter. Volume of cement will be mass of cement divided by specific gravity of cement into 1 divided by 1000. Mass of cement is how much? 270. From where we got? Go back here. It is written here 270. It is written 270 here. For volume of fly ash, the volume of fly ash is equal to mass of fly ash divided by specific gravity of fly ash into 1 divided by 1000. Fly ash, how much we got? 115. We got fly ash as 115. So again, specific gravity of fly ash, they are going to do. You have to do the specific gravity test on the fly ash in the lab, and from there you got this value as 2.2 into 1 divided by 1000 comes out to be 0.052. Next is volume of water. Volume of water will be mass of water divided by specific gravity of water into 1 divided by 1000, which comes out to be 140 divided by 1. If you do this, no, again 0.140. Specific gravity of water is always 1000, so it's written here. Next is super plasticization. Here we are going to make use of 2%. Even as I mentioned, you can take 1.5% also. Again, depends on your site conditions and all. Yeah, therefore mass of chemical admixture will be, always remember, admixture we try to add in terms of percentage of the cementitious material. Okay, so that means 385 is the total cementitious material, isn't it? 385. For this, we'll try to put 2%. 2 divided by 100 will come out to be 7.74 cubic meter. Therefore, volume of chemical admixture will be mass of chemical admixture divided by specific gravity of chemical admixture into 1 divided by 1000. Mass we got from here 7.7 divided by specific gravity. You have to do the lab test, or you have to ask the supplier who is giving you a chemical admixture to tell him what is your specific gravity of the admixture that you have provided into 1 divided by 1000 comes out to be 0.07. That's it. Once you're done with this, next last one is volume in all in aggregates. To find the volume in all aggregates, whatever answer you got here, that is volume of concrete 1 minus volume of cement minus volume of fly ash minus volume of water minus volume of chemical plast admixture. If you try to do, no, whatever volume is left out, that will be my coarse aggregate and fine aggregate volume. So that is why volume of all in aggregate will be a in the sense this one, this a b c notation what they are given, minus b plus c plus d plus e, which will be 1 minus 0.06 plus 0.52 plus 0.14 plus 0. Comes out to be 0.715 cubic meter. So this is all in aggregate. This includes your fine aggregate and coarse aggregate. Therefore, if I want to individually find how much is coarse aggregate, mass of coarse aggregate will be F in the sense this thing, that is volume of all in aggregate into volume of coarse aggregate into specific gravity of coarse aggregate into 1000. All right. Okay, they have not done this. Okay, it's done here. Okay, therefore which will come out to be 0.715 into volume of course aggregate is 0.56, which you found it from here, volume of course aggregate, and then 2.74 you get it from the lab result. Otherwise they have given it here, you have to refer here. 2.74 is a specific gravity, and specific gravity of fine aggregate is 2.74. Yeah, right. So into 1000 you do 1097 kg is a coarse aggregate. Similarly, yeah, similarly for fine aggregate, okay, you take it up here. If you're getting confused, this should have come here, mass of fine aggregate. So for mass of fine aggregate, do the same thing. Instead of 0.62, instead of 0.56 here, this time you have to take fine aggregate. Fine aggregate is 0.44, so put 0.44 here. 0.715 is this value into 0.44 into 2.74 into 1000 comes out to be 862 kg. That's it. Now write down the complete thing. That is cement we need 270, fly ash we require 115, water 140, fine aggregate 862, coarse aggregate 1097, chemical admixture 7.7, water cement ratio is 0.364, right? That's it. After this, you know how to do this. You have to carry out the slump test. Make sure you're getting a slump of 100 mm. Do the compressive test on this and make sure you're getting a grade. How much? Greater than 40 Newton per mm square. Only then we can say that this particular mixed design, what we have done so far, it is fit for this particular condition and for all the data what we are given. Only then we can do the execution of this. So I hope you got an idea about this, how it has to be done. So in the next lecture, we'll try to see another one or two problem. So we'll see you back in the next lecture. Thank you.